Is 26th lecture, and we have discussed several methods of pulse width modulation techniques in this course so far, and now we are moving towards something which kind of encompasses everything. So we are kind of trying to generalize whatever we have learned so far, and from that general technique we'll try to have some maybe better techniques which can be used, or if we can develop better understanding why something was working fine, why something is not working fine, these things we will try to understand here. So just a quick recap before going further, what we have done so far. So our task is to convert DC voltage to AC voltage. This is what we are doing, right? Now what we have done, we have used single pole double throw switch for this voltage source converter. So we are trying to operate this SPDT switch. We are connecting the pole.
Sir, screen is not visible.
Okay. Yes. Thanks for the feedback. Now is it visible?
No, sir. It's showing green screen.
It will come. Is it there?
Yes, sir. Yes, sir.
Yes.
So our task is basically to have the DC voltage converted to AC voltage, right? Or DC power getting converted to AC power. And we are using this kind of arrangement. Single pole double throw switch for the voltage source converter to have the output at pole P changing between plus VDC by 2 and minus VDC by 2. This is what we are trying to have. Now, by using this switch, we have different ways. So what could be the first way is that in a very crude manner, you have the switch operated, let's say P getting connected to T1 for half time period and another half you connect it to T2. So this is something what is a square wave mode of operation. This is the most basic way where you can have the DC voltage getting converted to AC voltage. Of course, this has not many harmonics and you do not have any control over the fundamental. It is 2 VDC by pi fixed and all the other harmonics are also fixed. So then what we try to do, we try to introduce some degree of freedom within this waveform so that we can control at least the fundamental. So we introduced one notch over here in the center. So waveform symmetries we have discussed. So by maintaining waveform symmetries, several harmonics can be eliminated and then some phase for all the fundamental and the harmonic components can be justified or can be defined properly if you have all the four symmetries, which means the full wave symmetry, half wave symmetry, quarter wave symmetry, and if you have three-phase system, then three-phase symmetry. So by this we are able to eliminate lot of harmonics and then maintain the phase of the component properly. This is what we do. Then we introduce this alpha, let us say, and this becomes your corresponding angle, this pi minus alpha you can say. So this gives us freedom that our fundamental can now be expressed as this 1 minus 2 cos alpha. So we have liberty to choose the angle alpha according to our requirement for the fundamental voltage. So if we are running a motor, we need to have voltage going all the way from 0 to maximum, and so we can choose our angle alpha and we can vary our fundamental voltage. But the problem which came over here is that again, we don't have any say over the harmonics. So we tried to have more degrees of freedom and then we introduced one notch in the quarter cycle. So earlier it was one notch in the half cycle. Now there is one notch in the quarter cycle. That's the bare minimum thing what we can do. Okay, and as we keep on increasing the number of notches or number of switching angles within the quarter cycle, we have better and better waveform and we have more control over the harmonics along with the fundamental. So this is what we understood. Now this was one way we were doing in this manner, And then we realize that if we have liberty that we can switch this SPDT switch, we can operate at much higher frequency. So here what is happening? Only few times, let us say 5 times of the fundamental or 7 times of the fundamental or 9 times of the fundamental. This is what is your switching frequency. It's kind of restricted here. So it may be restricted because of several reasons. We have high power system, we have high speed system and so on. And we are trying to reduce the switching energy losses, or we do not have the capability to operate at such high switching frequency. So in all those cases, we were doing that. But for, let's say, low power system, we can operate our switch much faster. So if we are talking in terms of 50 Hertz system, we can operate, let us say, at 5 kilohertz. Then no need to go by this method. Then what we tried? We tried to go by realizing the sinusoidal waveform by approximating it to a staircase waveform. And these steps or the voltage levels, what we see over here, these are realized by operating the SPDT switch for each interval. So sometimes you connect to plus VDC by 2, sometimes you connect to minus VDC by 2, and on an average we get some voltage. This is what was the other method. If you operate for equal duration, the voltage is 0. If you operate for more positive duration, then the voltage is positive. If you operate for more negative duration, the voltage is negative. This is all we have seen. So each voltage level, what we have drawn over here, the staircase waveform, can be realized using this kind of operation. We are switching much faster. And the way to do this is you have this signal which can be called as modulating signal and compare it against a triangular carrier. So we have a way to decide the total time period. This is now fixed. And then based on where your modulating signal lies, it will generate the PWM voltage or gating signal according to that. Say if it is here, then it will be on for this much, off for this much duration. And then on for rest of the duration. Whereas for the second case, it will be off for longer duration and then on for smaller duration. This is basically width of this pulse is changing, and that is what is known as the pulse width modulation. This is how we are realizing, right? Understand the point? Fine, no confusion up to this point, right?
Yes, sir.
Yes, okay. This is what we have said as sine triangle PWM. Now we can have variations of triangular carrier based PWM. We can inject some harmonic, we can have some more things like bus clamping or some other methods. Okay, but altogether what we are doing, we are trying to realize a voltage level within this interval by having positive and negative pulses of voltage. So either it could be plus VDC by 2 or it could be minus VDC by 2, but it will ultimately give an average value of whatever voltage you are trying to realize. So the realizations what we are doing, whether in this case, in case of low switching frequency PWM or in case of high switching frequency PWM, these all realizations are done on per phase basis, which means we are realizing the voltage for R, Y and P separately. Of course, here the modulating signals are like 120 degree shifted, and here the waveform itself is shifted by 120 degree to maintain three-phase symmetry. Fine. But what we are doing basically that we are realizing the voltage for R alone, Y alone and P alone. And by maintaining the 120 degree shift, we are maintaining the three-phase symmetry. You understand the point here? Now, from this per phase basis realization, we are moving towards something which contains information about all the phases together. Let's say if we have three-phase system RYB, I would like to express this in form of a quantity which has information about all three. I need not say that my VR, Vy, Vb is so much voltage. I can say that this quantity, say Vs, and that's all. That itself will tell what is the information, what is the value of VR, what is value of Vy, what is value of Vb. This kind of representation first I am looking for. You understand my point? So which is where we take help of the representation technique which is called space vector. Now, when I say space vector, what comes to your mind? What do you understand by this?
So vector rotating in a space.
Okay. Now my next question would be, what is phasor?
Phasor is a rotating vector with respect to
Space.
sir in time, considering the time frame.
Okay.
While space vector involve also the space.
This is some difference. Another thing is the idea about phasor is, yes, what you said is correct. Phasor is always rotating, whereas in a space vector, when we are representing the quantities, it could be stationary. There is no need for rotation. Understand my point? The resultant may rotate, but the individual quantities may remain fixed. So this is basically concept which is derived from the AC motors. So what do we have in AC motors? We have distributed winding. Correct? So this I have discussed earlier also. Let us say here we are keeping let's say our winding is distributed like that. I have shown as a lumped winding for each phase, but basically this is like more distributed, right? For better waveform. But to have understanding about the system, what we have said in case of no induction motor, we have seen that if we have distributed winding and we inject or we apply voltages which are time distributed to this system which is space distributed, we finally get the quantity which is called flux or MMF, which is rotating in space, the resultant quantity, right? So to visualize that, I mean, already this thing is done, you can revise from the previous lecture. Just to recap that thing, if you have just one winding, say this coil. So when I say dot, basically the current is coming out of the paper and cross is basically going into the paper. Okay. So this is basically the coil is perpendicular to this surface. Now, what will happen in this case if we have such coil? Where the flux would be? Yes, some response.
Positive axis.
Yes,
Correct? So right hand thumb rule you can use and you can see that it will be the direction of, or basically if you say in general, the flux will be lying in this axis which is perpendicular to both the axis and the coil, like this coil axis here, right? So the flux will be lying in this along this axis. And if you have, let us say I am feeding VR to this coil and VR voltage is Vm sin omega t, or basically for simplification you can take IR, which is Im sin omega t. So what will happen? The flux will be going along this axis. So at theta equal to 0, what will be the value of flux? Let's say that we are injecting the current directly. So what will be the value of flux? It will be 0, right? Yes or no?
Yes, sir.
You can unmute yourself. Here, I need little bit involvement from your side. Now, when your theta goes to 90 degree, what will happen? The flux will be maximum. Then again, when it comes back to 180, it will come back to 0. It goes to 270, it will be minus, maximum negative, and then it will come back to 0. So what is happening? The flux is moving along this axis, and which is what is called as pulsating flux. So pulsating flux means it is only going up and down along this axis. There is no rotation involved in this. Similarly, if you have other phases also distributed, each will have their flux getting changed only along the perpendicular axis. So let's say y is here and b is this, so something like here. So three fluxes will be basically changing only along their axis. And when you have a system which is basically applying voltage which is time distributed, let's say, or time shifted, so what happens? These different voltages are going to have peak values at different times. For example, at theta equal to 90 degree, the R will be maximum. So you will have maximum flux along this. And similarly, Y and B will also have their contributions. Now altogether, the resultant, if you see, so check the previous lecture, the resultant will appear over here for the case of theta equal to 90 degree. Similarly, you check for other angles, say for example, theta equal to 0, the resultant flux will appear somewhere, or if you are having difficulty in writing voltage, you can consider current instead of voltage. So for theta equal to 0, the voltage will appear to have peak around this. Then similarly for 270 degree, it will be here. So 180 degree will be here. Similarly, other angles also you can work out, and you will see that the effective voltage vector or the flux vector is basically rotating as you keep changing your theta. You understand my point? This is what we have in motors. This is what we have in case of induction motor or any other AC motor, if you take 3-phase, 5-phase, whatever. So this resultant flux is basically rotating, and which is what is giving you the principle of induction through which the motor is operating. Now this concept, here we are not discussing machine, but we are only understanding the concept which is used to represent other quantities in this form. For example, system of voltage, let's say what is written over here. Now, if we represent this in space in this manner, like how we have done for the flux, VR, Vy, Vb. So point to be noted over here would be that these axes are fixed, which means this is not rotating like phasor. This is a fixed vector which can change its value only along its own axis. It cannot rotate. And when we have this kind of arrangement, what will happen? The resultant vector which is coming out of these three voltages will have tendency to rotate similar to the flux. For example, again you can take theta equal to 0. You will find that R is 0, Y is negative, and B is positive. So a resultant vector will be appearing here. Similarly, you go for 30 degree, sorry, the 60 degree, it will appear. So here it's going to be, just wait. Yeah. So similarly, if you go for 30°, this will appear to be coming over here. At 30, R will be some positive value, Y will be some negative, and B will be some positive. And so the vector will appear over here. And then similarly, if you go for theta 90°, then the resultant vector, which means R is maximum, Vm, Vy is basically how much it will be? Some negative value here, and B will also be negative. So resultant of the three is too thick. The resultant of the tree will appear like this for theta equals 90°. You understand what I'm trying to say over here? So basically any multi-phase quantity, let's say whether it is voltage or current, we have kind of placed in the space in this manner. We have distributed in this manner. And with this, we are trying to have an understanding about the effective voltage vector or current vector, what is generated from this. So if you combine these three quantities, no, these are separated by angle 2 pi by 3, you can represent the effective voltage vector as this. You understand my point? Now this representation what I have written for this system, this gives the information about all three. If you know the magnitude and angle for this, you can tell what is value of VR, Vy and Vb individually. So that is the representation of a multi-phase system in this manner. Do you understand this point or there is confusion?
Yes, sir.
Clear, Ajay, or any confusion here?
Yes, sir.
Shambhunath?
Yes, sir.
So what we are trying to do over here is we are trying to have representation of this multi-phase system in terms of something which is called as space vector. So it is nothing but a mathematical representation. No, it's not necessary that we are going to feed this voltage to any machine or any generator or anything. It could be a grid connected system. It could be a simple three-phase load. No, it could be anything, not necessarily a rotating MMF kind of system. Here we have a multi-phase quantity which we are trying to represent in terms of a unified number in a unified form, and which is what is called as space vector representation. It's a mathematical form. So this vector, if you try to measure physically, it may not be there. You understand my point? This is only mathematical representation. And what we are finding out of this is that we have a fictitious vector, you can say, which is basically rotating at omega in the counterclockwise direction as you go from theta equals to 0° to theta equals to 360°. You understand my point?
Yes, sir.
Now, let us understand this little bit more. Okay. So when we have sinusoidal system. That means three-phase sinusoidal quantities are there, say voltage. Okay, it has gone worse actually. So any information about arrival to campus? Yes, no, what?
Sir, some of us are already here, and some more people are coming after Holi.
Who all are here? Tejdeep, you are here, I know. Who else? Nobody.
Sir, I will come, sir, on 19 March, sir.
That's okay. Who else is here?
Sir, I am here.
Hmm?
Sir, Sampan, I am here.
Okay, you have also come here. Okay, good. Fine. So what I'm trying to indicate over here is that you see this three-phase waveform what we have. So theta is basically changing from 0 degree all the way up to 360 degree. If you just add, no, algebraically what will happen? It will sum up to 0 because this is balanced three-phase system. VR, Vy, Vb will add up to 0. However, when we are applying this to any load, let's say which is star or delta connected or any motor or no grid connected system, this is not algebraically added in that system. This goes in a vectorial manner. So what we have basically, we have the resultant of the three getting added in this manner, what we are showing over here. So for example, you take these instants, what I have shown theta equal to 0, or say this would be 30 degrees somewhere here near the peak, 30 degree, then this would be something like 60 degree, this is around 90 degree. So what will happen that you will find the voltage vector is kind of shifting to different locations, and because this is varying very smoothly, each and every value on this waveform is available for us because we are representing it like this. So mathematically each and every point is available. So what happens? The voltage vector basically rotates on a circle. The tip of the voltage vector follows a circular trajectory. Fine, each and every point is there. Whichever point you would say theta, and then yes, you can tell that where the vector would be, right? So possibility for each and every point is there in this system. Now, this is not a necessary condition if you want to represent any system in this case. Okay. For example, let us say if I tell that my voltages which are there on RYB, they have only two possibilities. Say VR can be only plus Vm or minus Vm. Then Vy can only be plus minus Vm. And Vb can also only be plus minus Vm. There is no other value available in between. Now what will happen? How do we represent this system in that form, in a space vector form? So still we have the same way. We distribute the R by B axis similar to how we have done earlier. We have R axis, Y axis and B axis. Why I am keeping Y over here is because these axes are fixed. The observer is rotating. So observer encounters R and then Y and then B. You understand the difference? This is stationary. This is only an axis. nothing else. This is not rotating. What is rotating is the resultant quantity. So an observer which is, let us say, moving at angle at a speed omega. So what will happen? First it will encounter R and then Y and then P. And these are peak values I am talking about, similar to our three-phase system. If you start moving in this direction, you will have R peak first, then Y peak, then B peak. That's the meaning of this representation. Now what will happen if we have only these discrete values available for R, Y, P? So for example, if I say that at a given moment, my VR is plus VM and my Vy and Vb are minus Vm. So where my vector would be? Yes. So you can draw on this same axis, you can draw Vm along R. And then Y is negative and B is negative. So this comes along minus Y and minus B, minus Vm and minus Vm. What is the resultant of these three vectors?
Vm into 1 plus Vm into 1 plus root 2 along first one.
Vm into
1 plus root 2.
no. Say again. This is 60 degree, right?
Oh, yes, sir.
90 degrees. BDC of 90 degrees.
So the total will come as 2V,
2VM. Yes.
right? So which means in condition when you have this value for your system. Now this is not continuous number, right? This is not sinusoidal quantity. We are having only some discrete, let's say two values only, plus Vm minus Vm for R, for Y, for B. And in a particular case, we have this kind of values for R, Y, B. R is plus Vm, Y and B are minus Vm. So we are getting resultant vector along R axis and the magnitude is 2Vm. Now if I change this, let's say VR goes to plus Vm and so is Vy, whereas Vb remains at minus Vm. So what will happen to the vector now? I'll draw with black color. R is still positive, Y comes positive and B is now negative. So where the vector will be now?
It's 60 degree ahead of the previous vector.
Correct? And the magnitude will remain same, 2Vm. So how are you computing this? You are again using either you do this in this manner, drawing this, or you can compute it from this as well. So how this is represented basically? Any vector Vs is basically sum of, let's say, this is my axis and this is the perpendicular of that. I'm not naming it as of now. So what I'm doing, I'm taking R as a reference and then Y is basically shifted by angle 2 pi by 3. So it is added vectorially to this R. And then B is again shifted by 2 pi by 3 from Y. So again it is added vectorially to that. So every counterclockwise rotation by 2 pi by 3 or any theta, you are just having this unit vector e raised to the power j theta getting multiplied to that vector. Okay, magnitude remains same. The representation includes this e raised to the power j theta. So you can solve by this method also. Now, when you have continuous quantities, this will boil down to something like VR, then Vy by 2, Vb by 2, plus j times of root 3 by 2 times of Vy minus Vb. And this is what we know as our famous alpha beta transformations. Correct? So this axis, what we are drawing over here, alpha beta, is basically resolving this whole voltage vector in just two components we can call as real and imaginary, nothing else. Now when we have only discrete values for the voltages, still this is valid. Okay, that's why I am representing over here. Whether it's a sinusoidal quantity or discrete number, this is still valid. Now, what you are seeing over here is that when we are changing the values of VR, Vy, Vb, the voltage vector is kind of shifting its position. Similarly, if you have the values of Vr going minus Vm and same as Vb and Vy getting positive, say plus Vm, the voltage will appear over here. Magnitude will still remain as 2Vm. Similarly, if you go for another option where your Vr and Vy both are minus Vm and Vb is positive. Sorry, Vr is negative minus Vm and Vy and Vb are positive plus Vm. So your voltage vector will appear here. You understand my point?
Yes, sir.
Okay. Similarly,
Yes, sir.
another condition you take where your Vr is negative minus Vm and so is your Vy, but your Vb is positive plus Vm, it will appear along this axis. And lastly, this another option. So what basically these are, if you recall, our two-level voltage source converter is basically having voltage levels like this. It's only discrete voltage level what our two-level voltage source converter is having. What may happen? VRO may be only plus minus VDC by 2. VYO could be only plus minus VDC by 2. VBO could be only plus minus VDC by 2. So when we apply these voltages in the system, basically what we are having is that voltage vector is changing based on what voltage you have applied over here. You understand my point? Little bit more terminology which you are aware about. I will connect with that now. So if there is three-phase inverter, there are two possibilities for this R phase, two possibilities for Y phase, two possibilities for B phase, right? So total, this inverter can have 8 possible combinations. Correct? And if I represent, let us say, when I say any output is plus VDC by 2, I will call that state as plus. And if the output is minus VDC by 2, basically the lower IGBT connected, I will call that state as minus. So the inverter, two-level voltage source inverter, three-phase, we may have 8 possible combinations of these voltage levels. You understand my point?
Yes, sir.
Correct? Now, the possible voltages and the corresponding voltage vector, now let us try to have over here. Let us say we start with the state minus, minus, minus. All three are connected to the negative DC bus. That means the output at RYB is minus VDC by 2. Then we go to next state, come to next one. So I'm trying to rearrange in that manner where it can be seen as only one switching away. So which one is remaining? 0, 1, 2, 3, 4, 5, and then here it should be 6. 6 is basically minus y. Okay, y2 are changing. Just a second.
Fifth one is like minus minus plus B phase for fifth one.
Minus minus plus.
Before that one, sir.
Before that, this one you are saying, is it?
Yes, sir.
Okay. Then it becomes plus minus plus, correct?
Yes, sir.
Okay. So why I am arranging like this, there is a reason for that. So now we are trying to have our voltage vectors getting realized out of these states. So what will happen if we have all three connected to minus minus minus? Basically the voltages are along the negative axis and the combination goes to 0. So this is giving a 0 voltage vector at the output. Now when we have plus minus minus, we have the output coming as this, plus for R and minus for the Y and B. So overall it gives a voltage vector which is located here. Now we have to see that how to give the angle for this. Okay, maybe I have missed one thing to know, which I should have told for the three-phase case here. First important thing is to understand where is this theta. So as I told, theta is 0 here. So okay, fine, that is good. Angle 90 degree. So magnitude you are understanding, right? The magnitude is coming at plus VDC because this is plus VDC by 2, this is minus VDC by 2, this is minus VDC by 2. So overall this comes as plus VDC. Then again if you have plus plus minus, this will come as VDC angle 150 degree. So which will be basically plus along this and plus along this and minus along this. So overall it will give plus VDC over here. Then minus plus minus is basically along the y-axis. So something like VDC angle 210 degree. Then here it will be VDC angle 270. Okay, I'm not deriving the whole thing. Maybe tomorrow I'll take up this thing little better. Feeling little difficult in speaking. Okay, so okay, I think let us discuss tomorrow only. Little bit difficulty in speaking for me. So just remember that we will pick up from here tomorrow, that these are the voltages applied and these are the voltage vectors generated, and we will understand more about this, why this is happening and how it is located in space, and then discuss further. Fine.
Yes, sir.
Yes, sir.
Stop here. We will discuss tomorrow. Okay.
Yes, sir. Thank you, sir.
Okay.
Okay,
Thank
sir.
you.
Thank you, sir.